This is the second Jones Seminar of the year. We have our own professor, Jason Stauth, speaking. He's an assistant professor here at the Thayer School of Engineering. I think probably half the room took a class with him at some point. Jason received his BA in physics at Colby College and then came to Thayer as a 3-2 student many years ago, graduating from his BA in physics at Colby in '99 and then a Thayer graduate in 2000. After that, he went into industry, worked as an integrated circuit designer at Allegro Microsystems, where he designed magnetic current sensors and a variety of analog mixed signal products for about 3 years. After that, he decided to go to the West Coast, did his MS and PhD degrees at University of California, Berkeley, finishing in 2008, where he studied high-frequency power electronics and RF amplifiers. After that, he founded his own company. He was CTO of QV Sense Incorporated, which made submodule power converters for photovoltaic systems. And then it was not until after that, in 2011, when he was recruited to come and be a professor here at the Thayer School of Engineering. He works on high-density and integrated DC-DC converters, leveraging hybrid and resonant architectures. This past year, he received a National Science Foundation Career Award, which is one of the signature key awards that young faculty can receive from the NSF. And so it's a real pleasure to welcome him to speak to us about his research. So please welcome.
Thank you so much. Thanks, Brian. Thanks, everyone, for coming. How many former Engines 22 students out there? Thank you guys for coming. That's great. I love seeing you. Familiar faces. I'm going to talk about what will seem like a very, very large scope talk. So small-scale electronics for large-scale energy. I'll really be talking about a lot of our work in electronics, power management, specifically for a few applications in energy, and kind of honing in on the direction we're going in, which is really shrinking things down, making them cheaper, smaller, faster, more efficient. Starting off, I want to just throw up this slide. So this is a projection from the EIA released this year, 2016. By the way, these reports they send out are actually a good read. And with the way that Thayer and Dartmouth is looking at energy, it's probably a worthwhile thing for lots of people to read these. These are really good, broad overview of the energy landscape, not just renewables, lots of things. What we see and what they predict and what I think a lot of people believe is that going forward, we're going to significantly reduce our reliance on fossil energy. So there is a projection that's saying, coal is going to be decreasing. Maybe it doesn't appear to be a large decrease here, but actually this is a global projection. In the US, it's decreasing fairly sharply as natural gas comes in. Renewables are actually projected to be the fastest growing source of new energy over the next 25 to 50 years. And things like solar photovoltaics are even the fastest among the renewable sources of energy, even though they're only really right now a fraction of a percent of our total energy generation. If they can grow to 1% or 2%, that's a lot of growth in photovoltaics. Electricity use is actually projected to grow very, very rapidly. And that, you can see electricity becoming kind of the new commodity or the new way we're commoditizing all of energy, renewables, fossil energy. And so we see essentially more of a dependence on electric generation as a distribution of energy, less on fossils, more renewables, and solar photovoltaics growing a lot. Transportation is expected to have a very major change in the next 50 years. Here we have sort of our gasoline vehicles. If we look here at the 2015 timeframe, most cars on the road are gasoline or diesel burning, have diesel sources of energy. Hybrids are starting to grow, but this is projected to grow very rapidly over the next 50 years. It really just makes sense, both from an environmental perspective and from an economic perspective. over time, we're expecting electric vehicles, plug-in hybrids, and full electric vehicles to take a dominant share. And essentially, the takeaway from this and kind of leading into where we're going is that we're moving away from fossil fuels, gasoline, diesel fuel, oil, and towards kind of an electrochemical backbone of modern transportation. And that's going to be a big change. It's really kind of a tremendous thing to think about, that we can replace all of our transportation infrastructure with this electrochemical storage infrastructure. So kind of looking more detailed at some of these areas, and specifically I'm going to look at a few of these because these are the areas that we're working in. So solar photovoltaics it's been really amazing to watch photovoltaics over the last 10 years. So when I first got into PV was in around 2004. And there were a lot of projections, so from the DOE, from NREL, saying where we would get to with solar, with the cost of solar energy in the next 20 years, or by 2020, or even ever. And actually, one very positive thing is that the solar modules, which are the modules that actually absorb photons, turn them into electricity. We're actually at a cost point right now where you can go onto Amazon or like Google Shopping and buy solar modules at a price point that was said to never be achievable in 2004. So if you look at the projections people had, even the optimistic ones, we've actually already beaten that with the modules. The problem is everything else, this what's called balance of systems, and this is the aluminum, the cables, the racking, the connectors, the permitting, the inspection, the boots on the ground, people that have to go on your roof and actually install this thing. That's where the dominant source of cost is. Overall, it's kind of a nice picture because it's saying, in some ways, we've solved the really hard technical problem. I mean, it's not totally solved, but we've solved a very large portion of the hard technical problem. The rest of it's kind of an implementation problem. It's going to be interesting to see how that happens, how that progresses over time. But there remain a few issues with photovoltaics, such as, well, what we work on, some aspects of, can we tweak out the last few, say 2 to 10% of energy efficiency out of these modules, dealing with variability, the fact that that the sun only shines when it's sunny and clouds go by, and we have summer, we have winter, we have to deal with this. It's sort of motivating using energy storage as a mechanism to handle the variability. So electrochemical energy storage, kind of this other area that we're looking at, is also in a very exciting time. So manufacturing of say lithium-ion cells is at an unbelievable level right now. So Tesla has invested heavily in this. Manufacturing is absolutely in high gear. We're starting to achieve an economy of scale that we never thought would be possible with electrochemical storage. The sort of negatives are that they are currently in the space of dominating both the cost, the performance, the range, and this is more related to transportation, and the lifetime of a number of applications. And there's a lot of manufacturer and consumer uncertainty in electrochemical storage right now. For example, so the Samsung Galaxy, this actually turns out to be on the no-fly list right now. If anybody hasn't flown in a while, it just flew back from Chicago. Can't turn these on the plane anymore. But that's not nearly as bad as if this happens on your plane. So this is like the Boeing Dreamliner. They had a serious problem with some lithium-ion battery packs they had installed in the sort of the first generation Dreamliner. And if you ever want to get money from a grant manager, send them a Christmas card that looks like that. So there have been fires. And whether this is a real problem or sort of a hyped up problem, it is causing uncertainty, and it is something that needs to be addressed. And so there are some issues, related to reliability, mismatch in large arrays. I'll kind of get into that. And aspects of diagnostics. So how can we tell if a battery is going to fail? How do we know how charged it is, how discharged it is? How can we treat it nicely, make sure it lasts a long time and has good performance? And then just more generally, a whole host of applications that need energy and power. We have probably, I don't know, gosh, probably each one of us has well over 1 billion transistors in our pocket right now. All of these need to be powered, and there's a huge demand for managing energy flow in these sort of consumer electronics and off-the-shelf electronics. For example, you break open the iPhone 7, you look at the circuit board, and we're looking at, something like, I don't know, 30 to 40% of the entire area of the board is just dedicated to power. The rest of it is the stuff we think is important, like the radio chipsets and the baseband processor, the graphics processor. So power management, that's kind of where we're going with this. So power management, this is essentially driven by the need to take energy, convert it into a form of energy that's useful, to transfer power, deliver it at a potential or a voltage that's useful. It's often complex, and there are many opportunities and needs to manage the energy flow and alleviate systematic limitations in these areas. And more specifically, where I'm going with this is towards high-density power conversion. And when I talk about high density, what I mean is small. So we want to manage power, and we want to do it at a scale that's small for a few reasons. So one reason we might want to do that is in, say, automotive renewable energy, there's just tremendous cost pressure. These things have to be cheap. Energy is a commodity. If we're going to solve a problem, we must do it essentially for free. Reliability is a huge issue. And so we must do it both small, usually size goes with cost, not always, but sometimes. And then there are all these needs to solve systemic issues in energy areas. In sort of the portable communication device area, that's where we're talking about pressure on battery life, just the size of the thing. You're really only allowed like a vertical millimeter in height if you're going to design anything to go into a phone. Cost is also important, and then they just have a just ridiculous number of power management things that need to be done. And finally, sort of performance computing. This is our data center. So here's our data center. If you're ever gonna, it's a great place to work. So data centers are actually somewhere between 2 and 4%, depends who you ask. 2 and 4% of all of our electricity end load capacity goes into data centers. That's why they build them near the Columbia River Gorge, where electricity is cheap. And a data center is just a bunch of microprocessors banging away at 1 volt and 100 amps, whereas upstream at the hydroelectric dam, they're cranking out power at 100 kV or maybe even many hundreds of kV, and it needs to be processed, down converted again and again and again. Eventually it's at 1 volt and 100 amps, and that's 2 to 4% of all of our energy. So power management's a big deal there. And so in all cases, there are many opportunities to reduce energy consumption. It's often the limiting factor. It's been the limiting factor on the speed of microprocessors for about 15 years, is power. And then there is a dearth of experienced engineers crossing key boundaries that include power. And so I don't like to think of power in isolation. I like to think of it as needing to be sort of interdisciplinary. We need to cross boundaries, such as semiconductor design. Thermal is a big, thermal mixed with power is important. Things like mechanical engineering, manufacturing, and power. And actually the list can kind of go on. It's an area that is in need in many sectors. So I guess the first question I'm going to ask as I sort of get into more sort of technical details. So what is a transformer? Any Engines 22 student want to tell me what a transformer is? It's a transformer, Ben.
Transformer allows us to transform signals past things from one to another. It's going to allow us with power management to see it in your telephone lines.
Yeah, you're really close, and I'm going to say that's good. A transformer. So, I was kind of hoping someone would tell me it's a big, huge thing of metal with iron core and a bunch of windings, and you put voltage in one side, it comes out the other side. A transformer is a real general concept. A transformer is just a thing that interfaces across an energy boundary. And energy in equals energy out, but it allows us to change the potential. and the flow. And I'm putting this up there in like the engine's 22 cents, where it's really totally general. There's just a potential variable and a flow variable. Flow goes in. Actually, flow goes in here too, because that's the polarity we use in systems. We know it really goes out, so there's usually sort of a polarity inversion here. So a transformer lets us take potential from one energy domain to another, multiply it by some factor n, and then because of conservation of energy, the flow must be converted by exactly sort of 1 over n, so that if we multiply the effort times the flow on one side, the effort times flow on the other side is the same. So it conserves energy. But that's a very useful concept. Many of you probably use this concept. How many mechanical engineers use a transforming concept? Anybody mechanical engineer? Yeah, you don't know? So you guys use gears, you use pulleys, you use levers, rack and pinion. So we use them a lot. This is a very important concept. And you can fill in the variable. So take the analogy table, fill in the potential variable, fill in the flow variable. It's important in many, many classes of systems. It just happens to be very important enough that I can do pretty much my whole career just designing transformers. They're not the big ones made out of iron and copper, but it's very important in the electrical world because we need things we need to cross many potential domains, right? That concept of 100 kV versus 1 volt, we don't want to lose any energy. You have a question?
Yeah, you put a negative sign in the top right.
Yep, that's right. That's right. That's right. Yeah. Yeah, we don't normally do that in electrical engineering, but if you're a network theorist, this is actually the polarities I've used are correct. We could talk about it later. But basically it's because I've defined the flow as n on both sides, so you need the negative. So the flow is coming in, so the flow is actually coming out, but that's the negative direction on one side. So good. Thanks for asking that. That's good. Yeah. So let's get into power electronics. So here's a DC to DC transformer. I'm going to do this from a weird direction. But let's say I want to take a voltage, turn it into another voltage, a DC voltage, and turn it into another voltage. Well, what I'm going to do, I just thought of this. I'm just getting started, and I'm going to take this resistor, and I'm going to switch it, and I'm going to connect it to this voltage, which is called that 10 volts, and then I'm going to connect it to ground. So I'm going to connect it 10 volts to ground, 10 volts, or to 0 volts. And I'm going to just do the switch, over and over again at some frequency, some period. And I'm going to do it so a fraction of the time, D times the period I'm connected to the input voltage. Well, if I average that, well, the average of just a square wave at some voltage, the percentage of the time I'm there is D, then the average is just D times Vn. And so the power that I get to that resistor at the DC, at that average voltage, is just that voltage, dVn squared over resistance, just the equation for power. But when I look at it another way, every time I'm taking that resistor, connecting it to Vn, I'm burning Vn squared over R power. And so then if I average that, if I multiply that by D, it says that my average power, the total power I'm using is that. And then I take this and divide it by that, and I get an efficiency, which is the power I'm delivering at DC over the power total, and it's just D. And so if I'm taking it from 10 volts to 5 volts, it's 50% of the time, I'm 50% efficient. So that's not good. That's not actually a transformer. That's not obeying a transformer equation. Okay, and where's the rest of that power going? Here's the hint, I guess, is there. The other hand, anybody but Eric Hansen, tell me. So it's going into the frequency domain. It's going into the other harmonics. So the reason this worked is I just did the DC. So really what's happening, I'm doing the switching process. It's going into all these harmonics. It's at high frequency. And I just did the efficiency based on the DC, okay? So I'm losing all this power. And this is just all the switching harmonics, like the fundamental, the second harmonic, the third harmonic, versus duty cycle. Just one way to look at it. And so one way to build a better DC-DC converter is to get rid of those harmonics, get rid of them. And one way to do that is we'll just build a lossless low-pass filter. We know how to do that. Also from Engines 22, we know how to do that. We can just go and we built a bunch of these. And here's the transfer function for just an LCR low-pass filter. Actually, this, by the way, I borrowed this from Engine 22. This plot wasn't even taken from an electrical system. This is for a fluid system, but it has the same transfer function. So you see there's a lot of analogies going on. It basically passes all the power at low frequency, does something funny out here, and then it's blocking all the power at high frequency. And so when I take my switching process and I switch, I'm switching it between a square wave at 50% duty cycle. My DC term is 0.5. Here's all my high frequency harmonics. If I switch at a low frequency, most of these harmonics are under that cutoff. Mostly they're getting through. As I switch faster and faster and faster and faster, all of my harmonics are outside the cutoff. All of a sudden I have this is V out, it's a DC voltage. I'm mostly blocking the harmonics. Some are still getting through, but the DC is all getting through. And what I've just made is a DC-DC converter. Ideally, there's no other source of power loss I've drawn in this schematic other than possibly wasting some on that harmonic power. So actually, this is approaching 100% efficiency. And then I can do other things like here I'm just varying the duty cycle. I'm keeping the switching frequency high. The harmonics do all kinds of funny things out here. But you see here's my DC term, and it's mostly flat. So we have ripple, but I'm blocking that with that filter. So that's how DC-DC converters work. Here's the sort of really high-level abstraction that I kind of like. Sometimes I like it, sometimes I don't, but I like it now. So DC-DC abstraction, one way to think about it is we have a source of potential, and I'm even keeping it general, but let's say it's voltage. I have a switching process. I'm going to switch that up. I'm going to kind of turn it into an AC waveform. I'm going to need some energy storage. I'm going to switch it, store some energy, and then I'm going to rectify it. When I choose to, when I want to, I'm going to deliver it to the load. Then I'm going to switch it, store some energy, deliver it to the load. And this process of switching, storing energy, and rectification is the way in which we can make DC-DC converters. It's what they, and at lunch we talked a lot about this. This is what they lacked in the time of Edison. And if they had it, we might not have it, an AC grid. Okay, so considerations of this. Efficiency. So efficiency, resistance. If I'm transferring power, or if I'm conducting energy, or say current, electrical current flowing through resistance is going to be a loss. So we think of like conduction loss, which is related to flow of energy. Frequency-dependent losses. I'm switching, so I lose energy. I can lose energy from switching, and then I can also lose energy in passive components. In this storage process, they're not perfect. If they were, we would be very happy. Well, I can model a DC to DC converter this way, and this is where it starts to get a little circuity. But here's a nice model for a DC-DC converter. This is an ideal transformer, just 1 to D. That D is just the conversion ratio, like 0.5. I'm stepping it up, I'm stepping it down. I have an effective resistance that can be used to model the losses from flow, from current flowing through the DC converter. So I put a current load on here that flows through some kind of output impedance of this DC-DC converter, causes loss. And then this is sort of leakage and or frequency-dependent loss. So we kind of think of it kind of in two ways, conduction loss and sort of this frequency-dependent loss that we will have because of this process. And then considerations related to density may include things like, how much energy do I have in those passive components? The more energy I have, then maybe I can switch slower and I have less switching loss. How much of that energy that I have in the passive components can I actually use? It may have a lot of energy density, but I might not be able to access a lot of it. That will come up later. And then how fast can I switch? Usually the faster I switch, the less energy I need to store. So all important things. So then past decades. So this is a very quick snapshot, what people have done for 40 years or so. So these are topologies of DC-DC converters. This is the buck converter, okay? This is the same one we just went through. Hopefully not, maybe painfully, maybe not. This is the buck converter. We're switching. We have an LC filter you can look at it lots of different ways, to block the harmonics, to let the DC through. A boost converter just takes a lower voltage and steps it up to a high voltage. And then a buck boost kind of takes a voltage and can move it up or down, hopefully efficiently either way. You can kind of see these are sort of switching cells. I've just moved where I have the same components. I've just kind of moved them around to create those. We can build lots of DC-DC converters. We can build things with transformers that are truly isolated. We can really switch, create an AC waveform, put it through a transformer, rectify it on the other side, turn it back into DC. Yeah, you can absolutely do that. But you can also do crazy things like the Chook converter. You can do lots of things. There's lots of DC-DC converters out there, some with isolation, some not. One thing you see most of them have are these inductors. Inductors kind of everywhere. Inductors, transformers, those are all magnetic components. Magnetic components are great. And is Charlie here? Yeah, he is good. Okay, magnetic components are awesome, but we want to this underlying thesis of this work will turn out not to get rid of them, but let's start off by saying let's just get rid of them. So one thing you see, go to a DigiKey, just go search for some capacitors and inductors. Those are our two passive energy storage elements in the electrical domain. Just look for a capacitor, find its voltage, find its capacitance, do 1/2 CV squared, find out how much energy it can store, find out how much it costs. Do the same with an inductor, see how much current you can jam through it, find its inductance, do 1/2 Li squared, find out how much it costs. Oh, one thing you start to see, this capacitor stores 1 millijoule, 1 times 10 to the minus 3. It costs about a penny or two. This inductor stores 3.2 nanojoules. And actually, these are good inductors. I'm not like just choosing crappy ones. 10 to the minus 3 versus 10 to the minus 9, 6 order of magnitude. Well, higher energy density for the capacitor. And depending on how you slice this, it's 6 to maybe a good case, 4 orders of magnitude difference. Capacitors store a lot of energy. There are good reasons for that I'm not going to spend a lot of time on. But there have been some other studies that were actually basically just the same thing I did. They just mined a database. Look for a bunch of capacitors. These are capacitors. These are inductors. This is size over energy. Okay? You'd like it to be small. This is cost over energy. You'd like it to be small. Capacitors are both cheap and small for how much energy they store relative to inductors. Okay? It's a nice little data point. So in the past decade, there's been one of probably the most exciting, at least in my opinion, but you don't have to trust me on that, areas of power management has been in the area of switch capacitor DC to DC converters. Kind of because for many years, I think people sort of thought, we've got this all sorted out. We're just going to build buck converters and we'll just make them a little better and a little better and a little better and a little better. But then some people came along and said, actually, these things are pretty good. Capacitors store a lot of energy. You can integrate them into a chip. You can build all kinds of architectures with them. You can move energy around. This is kind of back to that same behavioral model that I showed you earlier. So they have a lot of energy density. You can build lots of cool architectures. You can interface low voltage switching devices, so like, semiconductor level, like Moore's law scaled CMOS devices, with capacitors and make really cool architectures and move energy around using capacitors. No inductors. Inductors tend to be big, much bigger, more expensive. So there's a lot of nice reasons why they're good, and many topologies possible. Another reason they're good is that this is the Cockcroft-Walton multiplier. Anybody in particle physics? Probably not. So this is a switch capacitor DC-DC converter. This is one of the more, well, not even very famous. People don't really even know about this thing. But it's this one. They got a Nobel Prize out of this. This was the first device able to achieve a voltage high enough to accelerate particles fast enough to create an artificial nuclear reaction. And this paper is really, really good. You should, it's excellent. It's really interesting. They tell you exactly how to build that. And so how does switch capacitor DC-DC converters work? It's actually going to be relatively simple, maybe even simpler than the buck converter. So here's how they work. So take a capacitor, connect it to a voltage source. The capacitor stores charge, C times V. Now take it, connect it to another voltage source. It stores charge, C times V. If the voltages are different, V1 minus V2, if it's a different voltage, there's some charge flows. Okay? And then we do it over and over again at some frequency, some average current will flow between this voltage and that voltage. Okay? And then I can take the difference in voltage, divide it by the current, and it goes with like 1 over C times the switching frequency. And so the units of this are voltage over current, which we know is ohms. And so actually the model for this thing is that. It's a resistance between two voltage sources. Okay? This is a 1-to-1 converter. It's not doing anything super interesting. Actually, this ends up being quite useful, but not obvious how that's useful. But we have this model that there's like an effective resistance, and it goes with 1 over the capacitance times the switching frequency. Now let's make it a little more complicated. And let's add some dynamics into this. Let's say there's a parasitic resistance here and a capacitor. And now we're going to switch it back and forth, back and forth, back and forth. Well, what happens when we add the resistance? All of a sudden we get this like first order behavior. This is the current. We see it kind of like, oh, I switch it, it kind of decays, and then it kind of spikes up. I'm transferring charge one direction than the other. The voltage kind of follows this first order profile. As I switch faster, well, if I switch really slow, I'm settling out. All the charge gets transferred to the capacitor. As I switch faster and faster and faster and faster, what you kind of see is that less charge is getting transferred because the resistor is limiting it. But what you don't see is I'm doing it faster. I'm doing it more times a second. And so this process ends up following kind of a weird profile that actually, well, I'll just kind of put it up there. It ends up following the real R effective follows this hyperbolic cotangent. And hyperbolic functions are really cool. If you haven't used them much, they're really, really cool. So the hyperbolic cotangent just says like it's a really good way for one trend to just exponentially transition into another trend. Okay? And what this is sort of saying is that like less charge is being transferred per cycle because of that resistance. I'm not letting it settle enough, but I'm just doing it faster. And it kind of, what happens is that the effective resistance versus frequency, this is faster. Effective resistance does go down with this 1 over F switch times C, and then it just plateaus and you can't get any better. Okay? And this is where you're really limited by the resistance. Okay? So this curve is important, and this is effective resistance normalized to ESR, switching frequency over a thing. Well, I'm going to get into this is slow switching limit is when we're switching really slow relative to the time constant, and the fast switching limit is where we're switching really fast relative to the time constant. So this is like the fast switching limit. We're switching really fast. It's really relative to the argument that's in that hyperbolic cotangent. And actually, this is important because I think we're the first people to use this as the boundary between fast switching and slow switching. So it's a fairly minor contribution. It seems minor, but somebody had to define it, and I don't know why nobody had yet. So that's our profile. It goes down, it plateaus, it hits the resistance limited transfer, and this is just for this is a 1-to-1, and that's a 2-to-1 switch capacitor. So let's talk about resonant circuits. I'm going to go through this a little bit fast, but how does this work? So a resonant circuit, let's just look at a series resonant impedance. Many of you know how this works. I just want to find out the impedance of this thing. Well, at low frequency, a series resonant impedance. At low frequency, the inductor is like a short. Maybe the resistor doesn't matter. I mainly see the capacitance. It goes with 1 over j omega c. At high frequency, the inductor starts to matter. It kicks in. It's a positive reactance, j omega L. And then I have the resistance. I'm really kind of, if I add these three things together, you can see it in the math. Move the j from the denominator to the numerator, I get a negative. Kind of write it like that. And then let's kind of omega L is exactly equal to this 1 over omega C. That's the resonant frequency. What happens there is that this whole thing cancels, it goes away, and we have a resonant behavior where the reactive impedances are canceling. All I see is the resistive impedance. The sort of impedance of that circuit right at resonance is just the resistance. Okay, there's a reason I brought that up, and I wanted to introduce this. And then the quality factor. The quality factor is really, well, we talk about it in terms of energy stored over energy lost per cycle, or we talk about it in terms of sort of reactance over resistance, or 1 over R or characteristic impedance over R. Lots of ways to look at it. But here, the important thing is it's sort of like the distance between these asymptotes right there and the resistance, that's the quality factor. So it tells us how much that thing kind of peaks. Well, we're going to use that and make switch cap circuits better. And we're just going to just do a simple augmentation of switch cap and put an inductor there. Treat it like this. Put a square wave across a resonant tank. And what you see here, I'm just showing the admittance. I'm going to kind of skip over this a little bit. Basically, what you end up with in a resonant circuit, if I drive a square wave across it, is I end up with a sinusoidal current. The resonant transfer function will pick out kind of the fundamental component of that voltage square wave, pick that out, and that's what comes through as the current. The fundamental magnitude of that voltage is going to go with like a 4 over pi times the amplitude of the square wave, and then the current is that voltage divided by the resistance right at resonance. And so my current that flows at resonance goes with kind of 4 over pi VA over R. And so when we do the sort of the resonant switch cap, we do the same thing we did with switch cap. Only we have a sinusoidal current that flows instead of this exponential decay, okay? And how do I get the effective resistance of this? Well, I integrate the charge that flows each cycle. And so instead of integrating kind of a decaying RC, I integrate a half wave of a sine wave. So I have a half wave sine signal of current goes in, a half wave sine goes out. I integrate those, and to find the charge, I find the average current by multiplying charge times the frequency, and then I do some manipulations. A bunch of stuff falls out. The effective resistance of the resonant circuit ends up going with just some weird thing, pi squared by 2 times the resistance. So no capacitance, no inductance, no anything except for a constant and a resistance. It's actually sort of a very different approach or a perspective than switched capacitor, because the performance is not limited by the reactive component. The main focus is just on the resistance. It's limited by the resistance, and that's good because it's telling us we're looking at the right thing. We're looking at loss. How much energy we can transfer is really now a function of loss, not some weird thing like capacitance and frequency. And so if I plot that R effective curve on the same sort of scale, here's my switched capacitor, goes with 1 over FC, plateaus at the ESR. My resonant circuit does this funky thing where it comes down here and it hits this limit, and this is really that same kind of pi squared by 2 times R. And what you find out is that the resonant circuit essentially is using the quality factor to reduce the effective resistance. So if we take the switch cap circuit at this frequency, we add an inductor and resonate it, we get down to a point that is exactly the quality factor lower in resistance. That's good because it means we have higher efficiency. The same thing is true. To get to the same effective output impedance of the converter, we could switch at Q times lower frequency. And many ways to look at this. Effectively, what we're doing is multiplying the voltage on the flying capacitor by a factor of Q. We're increasing the utilization of that capacitance, the energy density of that capacitance by Q squared. And what we have shown is that this benefit of Q holds true for all resonated converters. I guess you would expect it to, but it's not actually that easy to show that is in fact true, that this same benefit is true in all resonated switched capacitor converters. And so that kind of goes into just sort of the higher level, like sort of generalization of our work. So we're broadening this out and this whole family of hybrid and resonant switch capacitor converters, where we have a switch capacitor stage, some kind of inductance to either resonate or soft charge the switch capacitor stage. It has many, many advantages. The one major advantage that we talk about a lot is that one way to think about this is we use a switch capacitor stage to step voltage down by a great margin, and then we just use an inductor to support that final voltage conversion stage. So in other words, we can use a smaller inductor because we think of the volt-second product. How much energy the inductor needs to store is dramatically lower. So limitations and realistic considerations. So these include things like, okay, I told you we'd get rid of magnetic components, but actually we just really quickly, we brought them all back. So we need them. We need to treat them. We need to figure out how much loss we will get from these components, how much size overhead they will have. We also have a need for explicit bypass capacitances, because when we're resonating, we need a low resistance loop for current to flow in. So those are both important things. And then there are also practical limitations on interleaving, and I'll tell you what that is on the next slide. Interleaving is a technique that is sort of well known and used a lot in DC-DC converters. My student Chris was kind of the first one to really explore this in resonant switch capacitor converters. The idea is kind of like we're going to take one converter and split it up into some number of smaller converters, and now we're going to operate them out of phase so that current just gets pulsed in every portion of, instead of it all coming in at once, we segment smaller chunks of it coming in over time. Okay? So interleaving just lets us spread out the impulsive current flow. And basically what it does is it lets us reduce the ripple, the variation in the voltage and the current waveforms when they get to the output. The main benefit of it is that it lets us use less energy storage at the output. We don't need as big of a capacitor at the output to filter that pulsing current. So if we interleave, we can use a smaller capacitor. So, and ultimately, that gives us better utilization of the area or the sort of the volume of passive components we have. And I'm going to move past this one. That's a very interesting plot, but I want to talk about it. So next thing I'm going to talk about is how do we optimize these things? And so this is some work by Sarah Pasternak. So one way to look at optimizing DC-DC converters is by saying like, oh, we have conduction loss, we have switching loss. We want to balance these two things out. Most of our resistance is dominated by semiconductor devices. And so we extrapolate like how much resistance is there per unit of width and how much capacitance is there per unit of width. And we get these device figures of merit, the specific on resistance and specific gate capacitance. And after some brutal math, we actually were able to solve this for switch capacitor converters, which hadn't, by the way, been done before. And so we came up with some nice closed form solutions for the optimum sizing of all of the transistors, the optimum frequency, and the minimum power loss. And kind of the interesting things we see here is that it all goes with this device figure of merit, the load current, flying capacitance, and these weird constants that are actually the solution of a transcendental equation, which was the key to solving this. That was very interesting. For a resonant switch capacitor converter, it's a little different, but a little even simpler. We have these closed form solutions that say, I'm just going to look at this one. The minimum power loss goes with stuff times the square root of frequency times the device figure of merit. Look at this equation and tell me what the optimum switching frequency is. How do I minimize power loss as a function of frequency? Frequency just goes to 0. Okay? So that's funny because that we know that's not true. Okay? So what has happened here is that when we did this, we used an ideal inductor model. And that's actually an interesting first step. Here's a perspective on a totally optimized switched capacitor converter where I'm varying the frequency. This, by the way, is our minimum power loss point. And this is our totally optimized resonant switch capacitor converter versus frequency. We see basically that the benefit between the switch cap and the resonant switch cap just increases the lower in frequency I go if I have an ideal inductor. But what I haven't factored in is that inductors are not perfect, okay? And an ideal, totally lossless inductor, what's happening as I'm going this way is I'm using more and more inductance to resonate at a lower frequency, and I'm cheating. So if I use a real inductor, as I use more and more inductance to resonate at a lower frequency, my losses go up because I have more and more DC or AC resistance. I have more loss. And so what we have found is that you get this interesting trade-off between, these are real inductor models. Use a larger inductor, it pushes you down like that. Use a smaller inductor, it pushes you up like that. Kind of an interesting thing is that we found that the optimum point is exactly 4/3 above the ideal point. There's a few asterisks behind that to explain what I mean, but you can follow it. If you're optimum, you should be exactly right above that curve. Depends a little on your inductor model. So here's some just like prototypes we put together. Quite a few that we've done. This is a 2-to-1 resonant switch capacitor converter. This was mostly Kapil Kesarwani's work. We built this in a CMOS process. We have we have a nice process where we can put inductors directly on the surface of the die. This thing is 2-phase interleaved. It runs at about 50 megahertz. I will spare you the details on the circuit. The thing I will talk about is that this is sort of the metric that people use for really high density DC-DC converters. This is power density, saying like how many watts can we process per unit of millimeter squared of area. And this is efficiency. And this is sort of the historical trend for switch capacitors follows this direction. These ones out here use very, very exotic technologies. For example, this is probably a $5 million mask set, 32 nanometer with a deep trench capacitor at SOI. So this is where Kapil's work ended up being. And this isn't as good as that, but it's very, very interesting because it's in a completely low-cost CMOS process. It's like $100,000 masks versus $5 million masks. But it does use inductors to resonate, but it gets something like 85% efficient at, like, I don't know, 0.6 watt per millimeter squared, which is a very nice number for a switch capacitor design. This is Chris Schaaf's design, kind of following that up. We built now a 3-phase resonant switch capacitor converter. Instead of actual explicit inductors, the inductors are actually just traces on a printed circuit board. So we go down through a printed circuit board, trace over, back up. They're about a millimeter square cross-section, and there are 3 inductors here. And so where did this one end up? Okay, looks like a little bit better than Kapil's, but no, this is a log scale in this axis. So it has a good amount. It was something like, okay, at close to 1 watt per millimeter squared, 85% efficient, almost 90% efficient, a little bit lower. So it's a nice set of results. And then I am going to move to one last example here. So the thing I want to talk about last is our work in battery management. And so this is some work that's been done by Eric Den, Chris Schaaf, Keith Moffett. And we've talked a bit with Tesla on this. So here's the Tesla, and I borrowed a lot of these slides from Eric. So Tesla has a lot of batteries in it. They consume probably pretty close to all of the world's laptop batteries at this point. So 5-6 years ago, they were at 60% of the world's laptop batteries, but no one uses laptops with this kind of battery in it anymore. So they're kind of the last refuge for the 18650 cylindrical lithium-ion cell. They make these in very high volume. There are 7,000 of them in the floor of the chassis. They come in arrays of many cells in parallel and many in series. Thanks, Eric, for these slides. Capacity is limited by the weakest cell in the string. So if I take a bunch of batteries, put them in series, when I discharge them, if I have a cell that's underperforming, that one will hit its end of capacity first, and basically I have to stop using the string. When I charge, the weakest cell tends to charge fastest, and so that would limit the capacity of the other cells connected in the string. One solution is to take a resistor, put it in parallel with that battery, burn some extra power because that one's already fully charged, and that will let current flow into these cells and charge them. So it's called dissipative balancing, and they do that to equalize the capacity of batteries. Efficient power converters are we know about this, but they can move energy around. So if we take a DC-DC converter, we can move energy around in the stack, let them discharge all to kind of their minimum level, let them charge to their full level. It's a very nice solution, and it's been tried and known, and many, many people have worked on it, going way back, even to the lead-acid days. The problem is it's too expensive. Tesla doesn't use it. I don't think I can say that. Almost nobody uses it. It's too expensive. It's too large. The size, the cost mean that it's not making it in automotive, and really probably not much of anywhere. And we'll get back to that. There's a secondary thing that's really important in battery management, and it's diagnostics. And so it's like knowing, when am I out of charge? When is my battery going to fail? It's very nice. There are many methods to do this: logging the voltage and current, doing dead reckoning, measuring the voltage, current, temperature, strain, all kinds of things. What we're looking at is measuring the impedance of these cells. And so this is a technique called electrochemical impedance spectroscopy, where we look at effects that limit charge transfer across a frequency range. This is plotted on a Nyquist plot. It's a common visualization used in electrochemistry. So this work is really to combine, like, can we solve the cost and size limitation, and can we add these diagnostics into a battery management system? And rather than go into all the details, I'm just going to tell you the pieces involved in doing this. So the pieces involved a lot of control stuff. How do we do variable regulation with a resonant switch capacitor converter? Solving the actual control problem, doing things to change it from a MIMO to a SISO control problem, doing accurate data conversion and instrumentation. So we do a lot of work in analog instrumentation for both voltage and current. We started designing our own data converters. Eric has done a lot of work on embedded systems. So how do we really synthesize large blocks of transistors, or use FPGAs to do very complicated signal generation, to do a perturbation of the cell operating state, turn that into an actual impedance measurement using something like a direct conversion radio architecture. So this is the result of Eric's first board, and so this is his whole test board. It's all built in discrete components. That's the power right there. Power is relatively small. This is some test measurement he did to look at how does the impedance change over state of charge. We also worked with Princeton on this project, and we collaborated with a colleague of mine there to benchmark this last prototype against sort of a $15,000 laboratory prototype. Showed it's in good agreement. Where we went after that was to design an integrated circuit version of this. And this is the integrated circuit. So we took a lot of those concepts and we built a new resonant switch capacitor architecture, a lot of interesting new techniques there. Assembled the caps on top of the die, have some very interesting things going on there. So here's the sort of the new test setup. This is that IC mounted on the board. We're able to sort of move current up and down the stack of batteries efficiently. We're getting some in the neighborhood of 95% efficiency, moving it up and down the stack. Comparing it to our discrete work, just kind of validating the difference between sort of the resonant architecture and more of like a buck converter architecture. We went from a 10 microhenry inductor to 100 nanohenry. That's a factor of 100x, both in the inductance and the volume of the inductor. The area went down by a factor of 10, which is sort of driving with the volume of 100. The efficiency actually went up in our integrated circuit version, which was equivalent to about 40% lower loss. So this is really just kind of a very quick, I know I'm pretty much out of time, very quick progression of just how our research has gone. So I didn't talk about it a lot. We did a lot of work in photovoltaics early on. This was sort of our first work. This is all to scale, by the way, these things. So we took this thing, we shrunk it way down to about an inch square from about 10 inches square. This is Capil's power delivery DC-DC converter. This is Chris's, the chip is right there. And this is our work in battery management right there. So really, this is kind of just this trend towards making things smaller, more efficient, towards this millimeter cubed regime, where we can really leverage both Moore's law, novel passive components, and new techniques in power management. So last slide, bear with me on this one. Power converters, yes, they can be used for good. You guys know that that's like a real quote, right? And then, yeah. That's from the extended version. But I'll just pick up some buck converters. That's what happens when it's late at night. Okay. And evil. They can be used for evil. Weaponized moon stations don't design themselves. It's true. It's true. Definitely true. Okay, last slide. Okay. Yes.
One very broad, one very narrow. Do the broad. Power is generated typically 17.5 kilovolts, I think, all the way up, transmitted, comes down. Has somebody laid out the losses along the chain all the way down to the voltage?
Yeah, people certainly have, and they think a lot about that. I don't know those numbers offhand, but it's not insignificant.
Predominantly where?
So that's a good question. Actually, Charlie would probably know the answer better than I would. Yeah.
The other one, did you ever account for losses in switching with the MOSFETs?
Absolutely. Absolutely, we do. And I'm sorry I didn't go into so much detail on that. The losses in the MOSFETs are a lot of what we work on. So yeah, that's exactly what this slide's about. So here mostly what we're talking about is so extracting losses related to switches or MOSFETs, so it's related to resistance when they're on, and how much energy does it take to turn them on. Okay, and so that's the energy to turn them on is that, and it's a function of the width of the device. And here what we're doing is optimizing how big the devices are, taking into account both of those forms of loss. So, thank you. Question?
I was just interested, you made a great point how you have to use a real model of an inductor to get results that make sense instead of the nonsense one that you showed right there. How complicated a model for an inductor do you have to use to make your point right there?
That's a good point. Yeah, so I'd love to talk about that with you. So it kind of bifurcates. So if you really want to do an optimization, you kind of have to pick a regime in which you have a good model for an inductor. So we kind of work in two regimes right now. One is sort of a skin effect dominant regime, and the other would be sort of a DC dominant regime. When you have a sort of in between, it gets really tricky.
Where would the in-between be there?
So it wouldn't really be on this curve.
Okay.
What would happen is, depending on your inductor model, well, you'd have to look more specifically at what frequency you're at, which losses are particularly dominating. This is actually all skin effect dominant loss.
How does the true converter relate to this? I mean, the true converter is like a capacitance-based transfer value.
Correct. Yeah, so the true converter has a relationship to this. And by the way, I not too long ago found out that Slobodan Čuk is working on a lot of the same stuff that we're working on. Which at first I was like, wow, that's weird. And then I was like, that's actually a pretty good sign. So the true converter is sort of, I guess you can use it in a resonant mode. You don't have to. Mostly you're using a capacitor to block some voltage potential. Often you need some kind of a snubbing effect in a true converter. But it's a different architecture. But we're looking at, it's sort of more of extending what has really been done in switch capacitor, because it's really interesting how that can be done, and merging in sort of the soft charging resonant energy transfer piece.
So in the very beginning, you were laying out this transition from sort of petroleum fuels to this electric, particularly in transportation. What does that do to the center of gravity for the energy economy globally? Is it moving elsewhere? Who holds the cards on controlling production of these new components and raw materials?
Of an electrochemical-based transportation infrastructure.
Where's the center of gravity globally for that?
I don't think anybody really knows for sure. I mean, it seems to me that the U.S. is making a hefty push in that direction. But yeah, the good thing is there's not necessarily sort of a raw material issue yet, but I think that arises all the time. Tesla's invested $1 billion in a battery manufacturing plant in Reno. I think it'll be interesting to see how it shakes out, like who the players become, because it's obviously going to be a big deal over the next 50 years. I think electrochemists will be very highly paid for a period of time over the next 50 years.
Okay, Jason, I thought you were going to get into power-efficient lightsabers at the end there.
That is a...
talk to you about that, but
yeah.
I think we're out of time. So
All right, thank you. Thanks, everyone.